We physicists have been waiting for a century, beginning in 1916, specifically, for this. The image shows a nearby black hole, which may be one of the most charming and baffling phenomena in the universe. These enormous beasts rule the cosmos, exerting immense gravitational influence while remaining intangible for all intents and purposes. A black hole with a possible mass 2 to 4 million times that of the Sun has long intrigued scientists. However, despite decades of investigation, particularly over the last 20 or 30 years, our understanding has remained limited. Now, things are rapidly changing. Recently, Michio Kaku disclosed that we have finally received data allowing us to examine the contents of a black hole. This new information clarifies details that the scientific community may have overlooked from the beginning, offering fresh insights as we continue to investigate black holes and unravel the mysteries of space. Black holes are colossal and terrifying entities. Before diving into the specifics of Michio Kaku's discovery, we must first discuss the fundamentals. While we have a solid understanding of black holes, some gaps remain in our knowledge. In 1916, Albert Einstein published his general theory of relativity, which predicted the existence of black holes. However, the concept of black holes remained purely theoretical for another 50 years, until scientists finally found evidence of their existence in the 1960s. At that time, astronomers studying the star Cygnus X1 noticed a bright blue star emitting X-rays. Upon further examination, they realized this star was in orbit around a massive, invisible object. The X-rays were not moving randomly, they were being pulled into this dark entity. This discovery filled a major gap in our understanding, proving that black holes were not merely theoretical constructs of Einstein's imagination. This revelation prompted scientists around the world to study Cygnus X1, a black hole located in the Cygnus constellation approximately 6,000 light-years from Earth. This discovery was anything but small. Cygnus X1 is far brighter than the Sun and incredibly dense, exerting a gravitational pull so strong that even light cannot escape. This defining trait is why it is called a black hole. The very idea of a black hole is both captivating and terrifying. It represents a region of space where nothing, not even light, can resist gravity's overwhelming force. Anything that strays too close is pulled in and lost forever. This danger only increases the significance of studying them. Were black holes the end of matter, or just the beginning of something else? The answer turned out to be the latter. After the discovery of Cygnus X1, scientists began searching for more black holes. They estimated that nearly 100 million black holes might exist in the Milky Way alone. However, because they are incredibly difficult to detect, an exact count remains elusive. What is clear is that millions of black holes exist in our galaxy, making their study more important than ever. One fundamental characteristic of black holes is their relentless gravitational pull. Anything that enters a black hole is crushed into an unimaginably small point. In a way, black holes act like cosmic vacuum cleaners, consuming everything in their vicinity. If a person were to fall into one, they would be stretched into a single line before being completely torn apart. This horrifying process reinforces the idea that no one should ever venture near one. Although the nearest known black hole is about 500 light-years from Earth, that is still close enough to raise concerns. In 2021, scientists captured the first-ever clear image of a black hole, M87. This image was taken over several nights, with researchers compiling numerous photographs to piece together a comprehensive view. Their observations confirmed that black holes have three distinct layers. 1. The event horizon, the outermost boundary of the black hole. Once you pass this point, escape is impossible. 2. The photon sphere, a region where light orbits the black hole, trapped by its immense gravity. 3. The singularity, the core of the black hole, where all matter is compressed into an infinitely small point, causing the known laws of physics to break down. Every black hole is unique, yet they generally follow this three-layer structure. However, their internal mechanics remain one of the greatest mysteries of astrophysics. Traditional scientific methods struggle to explain what happens inside a black hole since conventional physics no longer applies. Scientists can only study black holes indirectly, by observing the radiation, gases, and dust surrounding them. Directly inserting a probe into a black hole is impossible, as anything that crosses the event horizon is immediately drawn into the singularity. This limitation forces researchers to rely on indirect observations and theoretical models. One leading theory suggests that black holes form from collapsing stars. When a star exhausts its nuclear fuel, it can no longer resist the inward pull of gravity. If the star is massive enough, it collapses into a singularity, forming a black hole. NASA researchers have focused their attention on the heart of the M87 galaxy, where astronomers observed an extremely hot, rapidly spinning disk of hydrogen gas moving at an astonishing speed of 1.2 million miles per hour. Logically, this gas should have dispersed, but it did not. This led researchers to conclude that an enormous, invisible object, likely a black hole, was anchoring the system. This black hole is estimated to be 2 to 3 billion times the mass of the Sun. However, black holes are not the only mind-bending phenomena in space. In 1963, New Zealand mathematician Roy Kerr used Einstein's equations to propose the existence of rotating black holes, further complicating our understanding. Kerr's equations introduced the concept of rotating black holes, or Kerr black holes. These rotating black holes have unique properties compared to their non-rotating counterparts. For example, the rotation of a black hole affects the spacetime around it, causing it to twist in a phenomenon known as frame dragging. This adds another layer of complexity to our understanding of black holes. As black hole research continues to evolve, scientists have increasingly relied on advanced technologies to study them, such as the Event Horizon Telescope, EHT. The EHT is a network of radio telescopes around the world that work together to capture high-resolution images of black holes. The groundbreaking image of the M87 black hole, released in 2019, was a direct result of this collaboration, providing the first visual confirmation of a black hole's existence. One key aspect of studying black holes is understanding how they influence their surroundings. Black holes can affect entire galaxies, including the formation of stars and the dynamics of the interstellar medium. The immense gravitational pull of a black hole can stir up gas and dust, leading to the formation of massive jets of material that shoot out at nearly the speed of light. These jets can extend for thousands of light years, significantly impacting the evolution of the galaxy in which they reside. In addition to their role in galaxy formation, black holes may also play a part in the eventual fate of the universe. Some theories suggest that the merger of black holes could eventually lead to the formation of a supermassive black hole at the center of galaxies. This could have profound implications for the structure and future of the cosmos. Despite the immense progress in black hole research, many mysteries remain. For example, scientists are still trying to understand what happens at the singularity, where spacetime becomes infinitely curved. Traditional physics breaks down at this point, and quantum mechanics has yet to fully explain how gravity works at such extreme scales. This gap in our understanding is one of the most exciting challenges in modern physics, and it may hold the key to a unified theory of quantum gravity. One of the most compelling aspects of black holes is their ability to warp time and space. According to Einstein's theory of general relativity, the intense gravity of a black hole distorts spacetime, causing time to slow down near the event horizon. For an observer falling into a black hole, this effect would be extreme, and time would seem to stand still as they approach the singularity. Another fascinating aspect of black holes is the concept of spaghettification. As an object gets closer to the event horizon, the difference in gravitational pull between its near and far sides becomes so great that it is stretched out into a long, thin shape, like a piece of spaghetti. This is a consequence of the extreme gravitational gradients found near black holes. As research into black holes progresses, scientists continue to push the boundaries of what we know about the universe. We are slowly unraveling the secrets of these mysterious objects, and each new discovery brings us closer to understanding the fundamental nature of space, time, and gravity. Ultimately, the study of black holes not only illuminates one of the most bizarre and intriguing phenomena in the universe but also holds the potential to answer some of the most profound questions in science. As technology advances and our observational capabilities improve, the mysteries of black holes may one day reveal the deepest secrets of the cosmos. Gravity gives the most accurate description of a black hole. He demonstrated that a black hole was rotating. A rotating black hole could not burst into a point, as anticipated, but instead, it would form a fire ring or a thin disk that would rotate quickly enough that external forces would stop this rotating thing from collapsing. The disk of matter is called the ergosphere, and the area around it is where physical laws begin to break down. However, the most fascinating aspect of the model developed by Royer was that it predicted the presence of an Einstein-Rosen bridge. This is a wormhole, also known as a hypothetical passage for travel through time and space that connects two distinct areas of the entire world or even two parallel universes. The idea is that one could disappear into a void instead of being crushed to ashes. They would pass through a passageway through the fire's ring and be released into a parallel universe through a white hole. To comprehend how this functions, we must take a look at the idea of spacetime in Einstein's theory. Our actual experience is not made up of distinct elements, but it is linked together to form a fabric with 4 dimensions, known as mass-warped spacetime. Objects cause this fabric to bend, creating a field of gravitational force that causes other objects to move in a specific direction. Now, imagine a piece of paper representing spacetime. When 2 points are placed on the paper and a line is drawn between them, it is a representation of how things move through space and time. But imagine being able to fold the paper in half and establish a direct route between the 2 points. This is the fundamental concept behind a wormhole, a quick way to get through spacetime between 2 distant points instantly. Wormholes are more than just a conceptual idea, they are a prediction of general relativity, despite the fact that no one has ever seen one directly. The reason for this is that wormholes are innately unstable and likely to fail quickly. However, the fact that there is an Einstein-Rosen bridge signifies that black holes are more than just enormous vacuums. They may also serve as entryways to places that could exist in different parts of spacetime. We could traverse the universe through a wormhole. Sadly, the response is most likely not right now. Even if we could, it is unlikely that we could stabilize a wormhole. We could utilize it to travel more quickly than light, but according to Einstein's special relativity theory, the speed of light is a firm limit on the speed at which anything can navigate through spacetime. Despite this, the wormhole and black hole theory, as access points to various parts of the entire universe or even to other times, has been an intriguing topic and long-running speculation among physicists. The chance that there might be ways to get around the structure of spacetime, making it possible to move across vast distances or even further back in time, could be revolutionary. One of the most intriguing concepts in this field is the CR wormhole. After Royer, the first mathematician described the equations of Einstein's gravity as applied to this kind of wormhole, essentially an imagined tunnel through spacetime, which could link 2 distant locations, like 2 distinct universes or even 2 distinct periods of time. The CR wormhole can be found in the same universe. It is shaped like a ring, similar to the mirror in the tale of Alice in Wonderland, and it might transport a traveler, theoretically, to a different universe or a different time, where the physical laws might be very different from what we're used to, but at the location, things might just carry on as usual. Despite the possibility of wormholes for traveling across galaxies or time travel, it is still a subject of discussion and debate among physicists. They have made the observation that wormholes, particularly black holes, could be difficult to cross or unstable because of the high radiation levels and subatomic forces that surround them. Einstein's supporters claim that Einstein's gravity equations are used to describe wormholes and black holes, but they don't account for quantum forces, which regulate subatomic and radiation particles. To comprehend their true nature, another explanation for these phenomena is needed to bring together the laws of quantum gravity. This is where the theory of everything comes in, a single theory that can combine both the gravity theory proposed by Einstein and Kaku's quantum theory. Working as a theoretical physicist on a theory of everything for a long time, and despite various versions of what this might be, the one that has shown promise is superstring theory. Gravity and radiation are combined in string theory. The theory proposes that subatomic particles are tiny strings that vibrate, and these strings compose the universe. Just like different notes in music correspond to various vibrations, the different particles in nature reflect the variety of vibrations of the superstring. An interesting aspect of superstring theory is that, as the string moves, it alters the fabric surrounding it, forming black holes, wormholes, and other awe-inspiring phenomena. This is how Einstein's equations can be solved, which signifies that superstring theory extends beyond Einstein's gravity theory and also explains quantum theory. Nevertheless, there is a catch. The additional dimensions of spacetime that superstring theory posits are so insignificant that we are unable to even directly detect them. Despite the theoretical promise of superstring theory, its practical implications remain uncertain. The concept of additional dimensions, those beyond the familiar 3 dimensions of space and 1 of time, suggests that our universe might be vastly more complex than we currently understand. These extra dimensions, though integral to the theory, are so tiny and compact that they cannot be observed with current technology or experimental methods. One of the intriguing aspects of superstring theory is that it proposes the existence of multiple universes, or a multiverse. This suggests that the universe we observe may just be one of many, each with its own set of physical laws. The interactions between these universes, and how they might influence one another, remain a subject of intense speculation and research. Another challenge with superstring theory is its lack of direct experimental evidence. While it offers a potential framework to unify all the forces of nature, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, no current experiments have definitively confirmed the existence of the tiny strings or the additional dimensions postulated by the theory. The energy scales required to probe these phenomena are far beyond what is accessible with existing particle accelerators, meaning that proving or disproving the theory might be a distant goal. Furthermore, the idea of a theory of everything is not without its critics. Some argue that trying to fit every aspect of the universe into a single, unified framework might be an oversimplification. Others worry that the pursuit of such a theory could distract from more practical avenues of scientific inquiry. Yet, the search for a deeper understanding of the universe continues to push the boundaries of what we know. As physicists continue to explore the mysteries of black holes, wormholes, and the nature of spacetime, the possibility of breakthroughs remains exciting. Whether through quantum gravity, superstring theory, or other innovative ideas, the ultimate goal is to find a unified description of the universe, a theory that could explain not just the behavior of the very small, like subatomic particles, and the very large, like galaxies and black holes, but also how these two realms are connected. In the future, advancements in technology or new experimental techniques might provide the means to test these ideas. Until then, concepts like wormholes, black holes, and the multiverse will remain in the realm of theoretical physics, sparking both wonder and debate among scientists and enthusiasts alike. The mysteries of the universe, no matter how elusive, continue to inspire a deeper quest for knowledge, one that could ultimately reshape our understanding of reality itself.